All right, let's take a look at breadth first search. So breadth first search, we're going to be using a queue structure instead of a stack. It's pretty much going to be the exact opposite of depth first search. In depth first search, we want to take a path and we want to take it all the way to the end. In breadth first search, we want to be taking as many different paths as possible because we want to ultimately find what is the shortest path to our goal. We're going to do this by checking uh, uh, all the children and then all those children's. But we're first going to deal with every single child first. So this is a more formal description of a breadth first search. And we're going to be using queues. So we're dealing with the same problem as depth first search, where we're exploring nodes and edges of a graph. And we're going to be dealing with it in the same way, in the sense that last time we dealt with a graph by representing it as an adjacency list. That is a pair of two elements, two vertices in a graph. And so the breadth first search algorithm is going to be particularly useful for finding the shortest path on a one-weighted graph. And we're going to be using a queue for our data structure to track which nodes we want to visit next. And so basically, if we have a graph that looks like this, how breadth first search would kind of look like is that we're going to be looking at each level at the same time. So we're going to be looking here, then here, then here, then like here, 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 and here, then like here, 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 and here. And so we're going to be essentially mapping out the entire graph, and we'll kind of have a more efficient path by the end of it, but we will also be like essentially visiting more nodes, usually. But we will know that we have like the most efficient solution. So we start by just adding our starting vertex, starting vertex to our queue data structure. So we push one to our data structure, and we also have, in the same case as in the same case as depth first search, we have a scene Boolean data structure where we keep track of which vertices we have seen and which vertices we haven't. So we start off with one, and we push one, and then we're going to pop one. And we know that this is in the goal, so we mark one as seen, and we're going to be pushing all of its children onto the stack, onto the queue. So we push 2, 3, and 4. 2, 3, and 4. And we're going to be popping from the front of the queue. So we pop from 2. We check that it's visited, so it becomes a green circle now. And we're going to be adding its children, but we're going to be adding its children. We're going to be adding 2, 5, and 6's children to the end of the queue. So even though we add 5 and 6, we're not going to be visiting those before we are finished visiting 3 and 4. So we add in 5 and 6, and then we pop from the queue. And the next vertex we're going to check is 3. And so we mark 3 as visited. We are going to add its children. So we add 7 and 8. But we add those to the end of the queue. So we're not going to visit those until we visited 4, 5, and 6. So then it's going to be 4, 5, and 6, and we push 7 and 8. Sorry. So, yeah, here we're at 3. So we're going to be adding its children, 7 and 8. We add to the back of 5 and 6. Then we're going to pop from the queue. So we'll pop 4. We'll add it to scene, so it'll be a green. 4 doesn't have any children, so we're not adding anything. But we're going to pop from the queue, so we pop 5 and 6. We pop 5. It doesn't have no unvisited neighbors. So we add 6. We pop the next one, which is 6. 6 has 9. We are going to add that to the queue, but we're going to add it to the back of the queue. And so then we just have 7 and 8. 9 is supposed to be in this queue. Okay. For some reason, they didn't add it till here, but yeah, we're supposed to have 9. Okay. Here we go. Because I was ahead of myself. Yeah, so this is 6. We had 9. Now we're at 7. Because that was at the beginning of the queue. And so 7, we're going to be adding the children of 10 and 11. We're going to mark 7 and 9 as visited because we visited them. But not before we visit 8 and 9. So once we get to 8, we are going to pop it. And we're going to add to visited. So it's going to become a green. And we're going to add its children. So we're going to add 11 and 12. And we're going to add those to the back of the queue. When we pop 9, that's not what we're looking for, but we are going to add it to visited. And since it doesn't have any children, we can just go to the next one. When we pop 10, that is the node we are looking for. So we will be ending our breadth first search, and we found an optimal path of 1, 3, 7 to 10. And that's an optimal solution. And so breadth first search is going to look a lot like depth first search, except instead of using a stack, we are going to be using a queue. And so the graph representation will look exactly the same. So we'll be using an adjacency list as well. And just like the breadth first search, just like the depth first search algorithm, we're going to be starting from the source node, and we are going to add it to the queue. And we're going to mark it as visited, and then we're going to explore the adjacent nodes. And we're going to keep doing this process until we've reached all reachable nodes. And we're also going to keep track of the distance. So we can do this in a myriad of different ways. So we can keep separate arrays to store these distances. We could pass it along with the breadth first search. We can store it some other unique way. But yeah, that will be an implementation detail. But once the breadth first search traversal is complete, you can find the shortest path from the source node to any other node by backtracking from the target node using the stored distances. And so now we're going to look at the code to implement this in C++. All right, let's get to it. So C++, we're going to be using a vector representation of the graph. We're going to initialize the source vertex, so that's the starting vertex, so we're going to initialize the target vertex. And so we are going to create a Boolean visited list, and this is going to keep track of which nodes we've been to and which nodes we haven't. We're going to initialize that to false. We're going to have num nodes, and this is going to keep track of the distance. But num nodes is really just going to be a counter of how big our graph is. And we're going to also have a distance graph, which is going to be keeping track of the shortest path from the start of the vector to that given vector. And we're going to also have a queue. And the queue is going to be a queue, which takes an int, and it's going to be called queue. So queue is going to be called queue. We're going to start by pushing the source, the starting vertex, to our queue. And we're going to be setting that vertex to true. And we're going to set the distance of the source to 0. Okay, so while the queue isn't empty, we're going to pop from the queue. So this is popping from the queue. We're going to dequeue. We're going to get the first instance, the first node in the queue. And then we're going to be checking the neighbors. So we're going to be traversing through the graph, checking its neighbors, and if we haven't visited the neighbors, if we haven't, if the node, if the pop node doesn't have any children, if it has children that we haven't visited yet, we're going to add that to the queue. We're going to set the visited neighbor to equal to true, and we're going to set the distance of the neighbor equals to the distance from of the current plus 1. So since we already start at 0, all of the neighbors of the vertex 0 are going to be plus 1. So yeah, that's how we keep track of distance. If the distance of the target is -1, so once we cycle through the entire algorithm, if there's no way to get to the target from the start, then we just simply output that no path exists from the starting vertex to the target vertex. Otherwise, we print out the shortest path, and that shortest path from the source to the target is going to be one of distance target. And so then we just simply backtrack from the target to the source to print the path. And how we do that is we simply create a iteration through the graph that tracks from the starting vertex to the end vertex. And so that's what this is. This is an iterator that will loop through the graph, and it'll print out the winning path. So we define the graph's edges. This is an example implementation. We have a graph of 6 nodes, and these are the adjacency lists. So there's going to be a relationship. There's going to be an edge between 0 and 1, between 0 and 2, between 1 and 3, between 2 and 4, between 3 and 5, and between 4 and 5. And the source is 0, the starting vertex is 0, and the target is 5. And when we call breadth first search, that's how we call it. We just call the function with this graph, the source and the target. So first, we want to create a graph representation of the prop. So that's this part where we're creating pairs of vertexes, and we're adding them to our graph with the edges. We create a vector of vectors where the graph is that's the adjacency list we're talking about. A vector of vectors of size num nodes, and each element of the graph is a vector that represents the adjacent nodes of a particular node. We implement the breadth first search algorithm, which starts from the source node and explores its neighbors in a breadth first manner. This graph is going to be an adjacency list representation of the graph. The source is going to be the starting node for the breadth first search traversal, and the target is going to be the node which we want to find the shortest path to. We also need a few data structures. So we're going to have a visited, which is going to be a Boolean vector to keep track of the visited nodes. A distance vector, which is going to be a vector to store the distances from the source node to each node. We initialize the distances to -1 for all nodes. And we use a queue to perform the breadth first search traversal. We start by enqueuing the source node into the queue, marking it as visited, and then setting its distance to 0. And so each one of that node's, the starting vertex's children, is going to be, those distances are going to be the starting vertex plus 1, and so on and so forth. And then we just need to start doing breadth first search traversal, which is going to be just dequeuing nodes from the queue, exploring their neighbors, and updating their distances. And then, sorry, this cat's freaking out. What is this cat doing? Sorry, my cat was acting up. So, yeah. Then we just iterate through the neighbors using the adjacency list. And if the neighbor's not visited, we enqueue it, mark it as visited, and update its distance from the source. To find the shortest path, we calculate the distances from the source to all reachable nodes. If the distance to the target node is still -1, that means that there's no path from the source to the target. So we would print a message indicating that. If there is a path, we backtrack from the target node to the source node to print the shortest path. Otherwise, we do a backtracking process involving finding the neighbor of each node and selecting the one with a distance of distance node -1, effectively moving backwards from the shortest path. Then we print the shortest path. Including the source and target nodes, and that completes breadth first search algorithm and finding the shortest path in the graph. Thank you very much for watching. As you can see, breadth first search is not so different from depth first search. And hope you've enjoyed this video. Thank you very much.